understanding the wireless channel. We will classify them as two types of effects. One is what we refer to as large scale and small scale. Again, we will describe and define those effects and then build our discussion around that. Shadowing is an example of a large scale effect. So we will begin by introducing the notion of how do we characterize these effects in a mathematical fashion, in a mathematical framework. That is the first part of today's lecture. Then we move into our characterization of the small scale effects. Quick update or announcement regarding the written assignments. Written assignment number 2 has been uploaded. We will have a test like you had for assignment test number 1 next Tuesday. Written assignment test, assignment number 3 will be uploaded on Friday along with computer assignment number 2. So please do keep up with the assignments. If you need help, please do not hesitate to ask. Reading assignments are being posted on a regular basis to keep track with our course. It would be very helpful if you are keeping up with the reading assignments, because that enriches your understanding of the entire picture. Okay, we move with a quick summary of what we have spoken about the cellular system planning. The cellular system planning requires us to fix a few parameters. One of the things is the cell area that we have to decide ahead of time. The second one will be the cluster size. Now, given that you can have a combination of these two, then we have an idea of how many clusters and therefore how many cells are going to be present. So the combination of these two tells us how many clusters are going to be present. That also tells us how many cells will be present. How many cells? One of the offshoots will be the cost. We don't look too much at the cost. Our interest is primarily in terms of the capacity. So the capacity is what we focus on. So once we have the number of channels available per cell, then we go back to our understanding of capacity and apply the traffic principles using the Erlang-B formulation. Cellular system is a blocking system, so therefore blocks calls are cleared. We do not have queuing, so therefore we use the Erlang-B analysis. This coupled with a traffic model. Traffic model has to say what is the approximate number of Erlangs each user will generate. So that is what we mean by traffic model. And of course you can have mixed models. You can have somebody is a heavy user, light user, but you must come up with some estimation of your total traffic based on the traffic model. So this then tells us the number of subscribers that we can support, and also the quality of service that each of them will see based on the C over I that will be again determined by the cluster size. So cluster size also has an impact on the C over I that you will see. Okay. And all of this we are exploiting the understanding of statistical multiplexing, the fact that all users are not asking for service at the same time, and therefore we are able to talk about a grade of service or a blocking probability in a statistical sense. So this is probability of blocking. And as I mentioned, probability of blocking is measured at the peak hour. So whichever is your peak traffic time, that is when you measure blocking probability, because there are other times when there will be 0% blocking. So again, this is a quick summary as you try out some of the examples that will be there in assignment number 3. These concepts will get reinforced. Now let's move on to our discussion on handover. Yesterday we introduced the requirement or the necessity for a handover because of mobility. User is moving from base station A, is moving over in a direction towards base station B. At some point he is going to be, the signal from base station A is going to be weak. Notice B is not a co-channel cell, because if the B were a co-channel cell, it will actually be creating interference. So B is another base station which is using an orthogonal resource, and therefore there is no interference. Basically you are looking at transitioning from one resource to another without them interfering with each other. The orange signal gives us the decay of the signal as you go from base station A towards base station B, and there is a receiver sensitivity that receiver sensitivity level below which you will the call will drop, that's the dropping point, but well before that you want to make sure that the handoff occurs. So we define a parameter known as the handoff threshold, and using the handoff threshold, PR min plus the handoff threshold tells us when you have to start looking for candidate base stations for handoff to. And once you have confirmed that this base station is consistently better than your own base station, then you do the transition. So that basically changes your signal to noise ratio from being a poor value to something that is provided by base station B, and therefore good signal conditions are maintained. We mentioned that there is a speech interruption time. Best way to visualize it is using this timeline. So if you think of this as time, the time when you started moving away from base station A, so there is some duration for which you are still under the coverage of base station A. And then you switch over to base station B, that happens at this point. At that point, base station B picks up. So there is a gap between when you switch over from base station A to base station B. That is what causes the interruption in your call. Since we are assuming it's a voice call, it's referred to as speech interruption time, but basically it's a break in your communication. So this type of handover mechanism has got a specific name. We break before make. You have to break the contact with one base station before you establish the next one. Break before make. And it also tells us why there is a risk of a call drop. One is you may not have finished the handoff process, which means that you have not finished the measurements, you have not given enough time for the network to figure out. So basically the process is not over. The second reason why a call drop can occur is that you have finished the process. The base station has told you now connect to base station B. Base station B tells you, okay, talk to me on frequency F2, time slot number 4. By the time you synchronize, there is too much delay has happened. Basically, mobile station, there was a limitation on the mobile station could not connect. That also basically, if the speech interruption time, for whatever reason, you did not finish the measurements or you did not resynchronize with base station B, that will result in a call drop. So whatever the scenario, if you have exceeded the maximum speech interruption time, the phone itself will trigger basically call drop. The network will then assume that you have terminated the call, and then unfortunately you did not terminate. You were actually wanting to hand off from one to the other. So this is a process that we have to be very careful about and make sure that we do not lose the subscriber in the process. So let's build on this understanding. Yesterday we spent a few minutes on the GSM control plane. Again, this is something that probably most of us never encounter, but from a understanding of the system, it is good to know how the service is provided. Call management layer is like an ISDN layer. It just worries about establishing the call and terminating the call. It does not know that it's GSM. It does not know that it is wireless. All it says is connect me to this user. Now, the layer that then figures out where this user is, that's the mobility management layer. Now, mobility management layer does not worry about which base station, which frequency, which time slot. That is not the worry of the mobility management layer. All it says is I have to reach this user, I have to keep track of this user, so therefore I'm monitoring the mobility of all the users in the network. Maybe more than millions of users I'm constantly tracking. Then below that comes the GSM specific, RF specific layer, which is called the radio resource management layer. Now that is the layer that then decides which base station, which frequency, which time slot, all of that, what power level to use, when do you initiate a call, when do you terminate a call, all of that is managed by the radio resource management layer. So again, you can see that how these functional layers work one with the other. Each one's task is very well defined. There are interfaces, and therefore the processing of a mobile user is in a very, very systematic fashion. That's the mobile system. Now the reason we introduced this was so that we could have an appreciation of the types of handoff that can occur in a GSM system. So basically we said that you could be changing from one base station to another base station under the same BSC, or you could be changing from between BSCs or between MSc, again there are different layers, and please do keep in mind that the mobility management has to keep track of all the users in the system, because ultimately that is what enables you to design and implement a very efficient handoff mechanism. So our understanding of the GSM control plane, very helpful, again just to understand the big picture. Mobile assisted handoff. As we saw, there are several measurements that the mobile does to help the system decide when to do the handoff. So mobile assisted, this is a very key aspect of the handoff mechanism, because the network depends on the mobiles to keep feeding that information, and that's how we are able to make the decisions at the right time. We also said that there are channels that are reserved for handoff traffic that is coming. So which means that you cannot do 100% loading of your own cell. So channels reserved for handoff. There's an impact on capacity. So there is a capacity will come down slightly, and maybe this question is obvious one. So in a cellular system, which is given higher priority? Is it an incoming call or a handoff call? Handoff call, because already I just now told you that there are channels reserved for it. So if a handoff request and a new call comes in at the same time, the handoff will be given higher priority. And the reason for that is? Okay, one is you want to minimize the call drops. There is a psychological element to it, because the cellular system is a blocked call cleared systems. That means if you get blocked, user assumes, oh, this is I will try again. But the quality of experience of the user is perturbed if suddenly you're in the middle of a call and then the call drops. So there is a quality of experience reason, QoE, and it has to do with users and user perception. So therefore the handoff traffic is given a higher priority over the new traffic that is generated. Okay. The other element was that we did mention that there is a fluctuation of the signal. We have not fully studied the signal fluctuation, but we recognize that because of the spatial distribution of the nulls in the propagation channel, there is a fluctuation, especially if the mobile is moving. So in order to avoid getting misled and making a handoff when it is not needed, you do RSSI averaging. Again, the window over which you do the averaging, again, a lot depends on what is your speed, and this is something that the network will tell you how much averaging needs to be done. Even on top of that, we do not want a phenomenon known as ping pong handoffs. So you don't want to sort of say, hand over me to B, then again say, no, I want to go back to A, go back and forth. So this ping pong handoff is something that we do not want to have, and therefore we have introduced a hysteresis. So you do not hand off until you have established that the new base station is higher than by a threshold, only then you will do the handoff. And likewise, so if you decide to going back in the other direction, you will hand off only when base station A becomes stronger. So there is actually a region over which the handoffs occur, and it will never be the same point where you hand off in both, the same point will not be where you will hand off in both directions. Where you hand off in one direction will be different from where you hand off in the other direction. And again, this is something that we will do a practical experiment to verify that this is indeed the case that happens. Okay. So any questions on what we had covered in the last lectures? These basically is a quick run through of the different elements, and the reason I repeated it was that it helps us build today's lecture. Okay. Now we move into the section that we wanted to devote for today, but maybe before that, let me just give one quick aspect I thought I would introduce. Now the RSSI as a function of let's say it's time. You're basically moving in this direction, so you're moving from A to B. RSSI we know will decay, right? Based on the propagation exponent, it will decay. Now if you are moving at a faster speed, now that basically tells you that you're going to go, your signal is going to decay faster. So this is your minimum level where call drop will occur. This is your threshold for starting the handoff. Notice that the time available for handoff is much less. So this is the time available for a fast user, whereas you have much more time available for a slow user. And so there is a need to keep track of the, so this is a slow user. The green line represents a slow user, the blue line represents a fast user, fast in terms of mobility. So again, keep in mind that a handoff is not just a single mechanism that is implemented that works under all situations. It's actually quite a complex one. As I mentioned, we have just sort of given you a flavor of the different elements that are present. Okay, now we want to move into another very, very important concept, and this comes from going back to saying what is wrong with the handoff mechanism as we have defined it. So when we go back and look at it, what are the weaknesses of this handoff mechanism? Basically, it is this, this particular interruption that occurs, because if that interruption increases, then the call drops. So the question that arises is, can I have a scenario where rather than having a break before make, can I have a system that does make before break? That means you establish the contact with base station B before you break the link with base station A. Very valid question. However, remember I mentioned right at the beginning, these are orthogonal resources. That means in the TDMA system, base station A is talking to you on a different frequency, base station B is talking to you on a different frequency. Time slots may be different. In fact, both may ask you to use the same time slot. Both. Now, how does a mobile talk to on two different resources? The only way it can do it is if it has two receivers. Okay, so this is not trivial from the implementation point of view, but it turns out in a CDMA system, CDMA systems are single cell reuse systems. The same resources, spreading codes are used in both systems. So this is actually possible in a CDMA system because one receiver can receive both the base station signals because both are transmitting in the same frequency. So that is a possibility for CDMA. So this actually was introduced in the context of CDMA. Introduced in CDMA, and it became one of the main reasons why CDMA overtook TDMA as the third generation system, was because you could do this soft handoff. Soft handoff basically says that you can overlap the users, you don't have to break one of them, and you can decide when to do the breaking of the system. So again, this is a useful visualization. It's a useful concept. Now, what is of course, there's a huge advantage because now there's no issue with call drop. You can decide when to terminate base station B. Now, what is the price that you pay for this? Does it come for free? As long as you are in that handoff region, you are using double the resources. So there is a reduction in capacity. Okay, and just like human beings, mobiles are also very greedy. They are very happy to be in soft handoff. They like, because they get more better signal to noise ratio, and actually mobiles left, they will actually be in soft handoff longer than they need to be. So again, there is a price that you pay in terms of the soft capacity. Okay, so and you also keep in mind that there is coordination needed between the two base stations because two different base stations are talking with this system. So here is a visualization of the mechanism that we talked about. Look at the bottom part of the picture where we introduce the hard handoff. You are connected to base station A with base station controller. Then as you are moving away, at some point the information is given to the other base station controller saying, okay, you have to take over. And the base station B starts to communicate, but there is a time gap between when you end with base station A and then you start with base station B. This is basically the hard handoff. That's the understanding of why speech interruption comes in and why there's a possibility of a call drop. Now, soft handoff, on the other hand, basically says you're talking to base station A, moving towards base station B, there is some point where both are communicating with you in a meaningful way. They are not causing interference to each other. They are both giving you useful signal. And then when you sufficiently are connected to the base station B, you disconnect. And of course, the disadvantages is that capacity will go. In order to have a efficient soft handoff mechanism, we must ensure that there is sufficient overlap. In terms of the spatial overlap of the coverage of the two cells. The disadvantage would be the reduction in capacity. Okay, so given that we are willing to take this reduction in capacity, what are some of the other aspects that we need to look into? The other aspects is the fact that let's take this situation where you have base station A, there's base station B, let's label them. This is base station A, base station A, this is base station B. They want to provide coverage for a mobile who's in the overlap zone. That's when you would actually be able to do soft handoff. Both base stations must receive, in this case, the voice information, because that has to be encoded. So that there has to be a coordination, and they must both transmit so that the base station, the mobile in the middle, gets the benefit of the soft handoff. So there is coordination between base station A and base station B. Now it could happen that the two sectors or cells, if you want to think about it, are actually the two cells that you're going from one cell to the other. The two cells are actually two sectors of the same base station. That can happen, because if this was the base station that was serving both, you moved from this cell to this one, it turns out that this is base station sector 1, this is sector 1, so this is sector 2. So basically this is sector 1 of the base station, this is sector 2 of the base station, and you are basically moving from sector 1 to sector 2. Now intuitively and from an engineering sense, this one should be an easier scenario, because there's only one base station involved. All it needs to do is, instead of radiating on this beam, I switch over to radiating on another beam. So this type of handoff, where you're actually going from one beam of base station or one sector of a base station to another one, is actually called softer handoff. Softer handoff. Now, are we limited to soft handoff between only two base stations? The answer is no. Because you could actually be in a location where 3, maybe sometimes even 4, 5 base stations can provide meaningful coverage. So in those scenarios, a CDMA system can actually do soft handoff with more than 2 base stations. So you could visualize a situation where there are 3 base stations. The mobile is sitting in the middle over here, and it says, oh, I'm very happy because I'm getting signal from multiple people, but I'm using more resources than I can. But mobile doesn't worry about that. You have to worry about it. Mobile is very happy. It's taking. So, but notice that in this case, 2 base stations and 3 sectors are involved. So if your mobile was in this point, it would be a soft handoff, because that is between two different base stations, 2 sectors of 2 different base stations. Now if your mobile was in this region, that would be a softer handoff, because those are 2 sectors of the same base station. Now mobile in this point is soft or softer? Soft again. And mobile in the middle is actually, it's a combination of soft and softer. So basically it's called softer handoff. That means there are, if you just say soft handoff, that means all are different base stations. If you say soft and softer, that means there are some transmissions that are coming from the same base station. Again, it's the reason I mentioned this is, one is terminology. If you've learnt soft handoff in the class and then you read softer and you're wondering, what happened, what is the difference, so there is a reason why it's called softer handoff. But more important, it's just that when you design it at a system and you start appreciating what are some of the nice elements about the system, and keep in mind that this is not easy with non-CDMA systems. So all of this actually comes from the world of CDMA. So TDMA actually cannot do this. What about OFDM? You answer me at the end of the course. It's a very interesting question. It is possible that you can do with neighboring base stations, but this notion of soft handoff is actually not very common even in OFDM. But you think about and explain that. Now I would like to just quickly introduce a little bit of terminology or nomenclature, so that you are familiar with the usage of these terms. We have basically covered whatever we need to cover from a basic understanding of the handoff mechanism. Sometimes you will hear the word horizontal handover. You know, one base station is up there, I have to do something, no, I can't do anything horizontal. No, that's not what horizontal is. Horizontal basically means that you're handing off within the same system. 2G to 2G, 3G to 3G, 4G to 4G. Okay. So when you don't say anything, it's assumed that it is a horizontal handoff. The reason you have even introduced the fact that you call something as horizontal, because there is something which is also different from this, that is a vertical handoff. So vertical handoff is a inter-system handoff. Another common terminology that you will find is radio access technology. Radio access technology. A horizontal handoff happens within the same RAT. This is within same RAT. That means if you are in 2G, you hand off to another 2G cell. Now the inter-RAT is what a vertical handoff is. Inter-RAT, from one radio access technology to another one. What are some common handoffs that we can see? You are probably connected to a 4G system. You go outside the coverage, it may drop you to GSM. So you may actually hand off your voice from 4G to 2G or from 3G to 2G. This is very common, especially when you move on a train outside of city metro coverage. Most likely you have been handed off to a 2G system. So that is a inter-RAT. But what is becoming increasingly important from a data perspective is another form of inter-RAT transfer, that is from Wi-Fi to cellular. Wi-Fi to 4G, for example. Now that is also an inter-radio access technology, because those are two very different systems. They also form the elements that. So this is another aspect. In the context of the horizontal handoff, remember there were several types that we characterized in the last class. Also mentioned it today. It is intra-BTS. You can have that. Well, intra-BTS is not correct, intra-BSC. Intra-BSC within the same but two different BTSs, then inter-BSC, then you can have inter-MSC. Okay, again, those are all nomenclature that you encounter. Horizontal handoff, inter-MSC, that means you know exactly what is happening. I'm going from 2G to 2G. I'm connecting between two locations that are being controlled by two different MSCs. Okay. Now the last part, that inter-radio access technology also has something known as an inter-mode handoff. Now that is a very tricky one, inter-mode, because that means I'm changing over from TDD to FDD. Of course, I cannot do anything soft here, it has to be hard, but so the landscape of handoffs is actually quite broad. There is a lot of complexity involved in it, but at a conceptual level, it is good for us to have this broad painting where we know the landscape of handoffs. Keep in mind that if you want to do, for example, an inter-RAT handoff, the mobile has to do a lot of work. Because if you're basically on one radio access technology using one particular receive chain, at the same time the infrastructure is saying, okay, go and do measurements on a 4G system, which means that you have to change your receiver in a sense, that because your bandwidth will change, your sampling rates will change, lots of things will change. You have to change all of those, do the measurements, come back to your old system, and then report. So again, you not only have to do measurements on 2 different channels, you also have to listen to 2 different control channels. Remember, all information from the network comes from on control channels. So you have to listen to 2 different control channels. You have to listen to the control channels of the origin radio access technology. You also have to look at the control channel of the target radio access technology. So again, listening to 2 control channels, doing lots of measurements in between your current operations is non-trivial. So therefore, any type of handoff actually makes the mobile a little bit more complex, and therefore more impact in terms of the design and the implementation. Now the last part is we must do something to help the mobile, poor mobile. And as guys are asking you to do so many measurements, you're asking you to do the changes. What is it that the network can do to help the mobile? So that is where we look at the help that it can give. So the network is constantly monitoring the received signal strength from the mobile. So long before you even get into the handoff zone, that before you trigger saying, hey, I'm near my threshold, the mobile says, okay, let me look at the trajectory of the RSSI that you are reporting. Okay, it's going down, and I know the rate at which it is going, so I can anticipate that you're going to ask for handoff. So again, the network sort of does predictive preparations for the, so there is a prediction. So there is a signal processing technique called linear prediction. Those of you who work with speech know that looking at the past, you can actually predict some things in the future, what the signal will look like. So one of the things that you would want to use in this information is how fast the user is moving. So that would be a measure of Doppler, because that tells you how fast the signal will change. It also tells you what has been happening in the past. So one is Doppler, one is past information. Why isn't Doppler alone not enough? It's a tricky situation. If this is the base station and you're moving directly away from the base station, then your Doppler will tell you the full story. But if you're going at some angle where your Doppler with respect to the base station, you're moving in a direction where the Doppler doesn't look very high, okay, but you may still be moving fast. So that is the tricky situation, because Doppler maybe you may be thinking, hey, this is probably somebody who's moving slow, but actually you're going to cross the handover boundary very fast. So there is a notion of Doppler gives you an idea of how fast you're moving, but you may be the Doppler measurement may say that you're not very. That's because there is a angle with respect to the base station direction, and you just have to be cognizant of that. So if you look at the rate of change, then you say, no, this guy's got low Doppler, but things are changing pretty fast. So therefore, you want to keep track. And as I mentioned again, mobility management has to take care of all of this. The monitoring of all these parameters are done by the radio resource management, and when you think that there is some anticipatory need for handoff, you trigger the mobility management layer saying, hey, you know what, I need resources in another base station, so therefore make sure the handoff happens smoothly. So this is the broad landscape of handoffs. And I'll just pause to answer any questions that you may have, because I recognize that this is probably the first time some of these terms may be somewhat new. Any questions on what we have spoken so far?
That angle is a parameter for more than Doppler if it's moving in that direction.
Correct.
Because we will have at first theta.
Yes, exactly. So that there's a velocity cos theta, which is what is velocity. True velocity is what we need for handoff, but v cos theta is what we will measure in terms of the Doppler.
But if we know the angle, we can know the.
Okay. So the question is, do I know the angle of movement? Sometimes not, because unless you start looking at the location of the user, you don't know. All you know is this person's RSSI is dropping very fast. And by looking at the signal that I receive from this user, I can guess the Doppler information. We will study about how Doppler can be computed from the received signal. So from the received signal, I measure the Doppler. I don't know what cos beta is. I just assume that you're moving slowly, because but that may not be the correct assumption. So Doppler alone does not give me the full picture. Okay, good. Let us now move into the next element. We have so far been talking a lot about system design. So system design, as opposed to what we are going to be studying now, system design is for a base station and large number of users. So it is a one-to-many system. So one BTS to many mobile stations in one cell, and then there are lots of these cells. So therefore, what we are looking at a large scenario, large perspective. Okay, and this is a scenario where you make several assumptions, and one of the assumptions is that the BTS is the master. BTS is the master, and it's a one-to-many communication. So on the other hand, the bulk of this course that we are going to be, once we have this systems perspective reasonably well understood, what we are going to be focusing on is the actual physical communication between the base station and the mobile. So this could be the base station side, this could be the mobile side. What is sitting in between is the wireless channel. And at this point, it is not a one-to-many system, it's a one-to-one system. So one-to-one system. You're not talking about base station talking to 100 mobiles. You're talking about one base station talking to one mobile. What happens to the signal that was transmitted by the base station? What happens? What is the effect on that? So at this point, it is a P2P, point-to-point link is what we are looking at, as opposed to point to multi-point was what previously the picture that we had in terms of making sure everybody has got good signal to noise ratio. At this point, you're saying, no, I want to know what is my signal to noise ratio, how can I improve my signal to noise ratio, how do I do that? So the focus on the channel is the primary takeaway from this course. So the focus will shift from system to a very narrow part of the entire communications chain. So focus on the wireless channel. Wireless channel. Now, if you were to say RF portion of the communication system, it would mean the following. RF is there in the transmitter, there is RF in the mobile. So the RF portion actually is this whole thing. Now, when we say RF, it is that, but when we say RF channel, I'm not worried about the power amplifier, I'm not about the filters, I'm worried about what is happening in this particular space. So the focus of the course is not broadly RF. Yes, it is RF, but it is RF channel, not the RF impairments that is caused by the power amplifier and other things. So again, let us be very specific. Now, what is different between this, what we are going to study, and what we have studied in digital communications? What we did for the most part in digital communications was we took the transmit portion, this is the transmitted portion, and we said that I'm going to represent my signal in terms of a complex baseband signal. Then we moved over to the receive side and said, okay, I now have the complex baseband of the signal with some impairment, noise, fading, whatever it was. So you basically skipped from transmitter to receiver using complex baseband as your representation. So again, it's very different. What we are going to focus on this course is not so much on the representation at the transmitter and receiver, it's what happens in the middle. Okay? And again, keeping in mind that the RF portion is a modulated signal, so it's a real signal, but it is going on quadrature carriers. So what we would represent is this portion of the signal, or what's happening in that, in complex baseband. So though it is not baseband, it is not complex, but for us to get a full understanding, what we would represent is a complex baseband representation of what happens in the RF channel. So again, I hope the nomenclature, the difference between what the digital communications course and the wireless communications course, why are both talking about complex baseband, and what is the difference between the complex, I've written it wrong, baseband. Complex baseband representation is what we will be picking up in today's class. Any questions on just the terminology or the nomenclature? Okay, now let us quickly look at what all do we have to study in this context of what happens between antenna to antenna. So what are all the aspects that will impact the signal quality, signal propagation? So first and foremost, we go in and say that, okay, in this big picture, there is one thing that we already have looked at, that is shadowing, because there can be a physical obstruction that is affecting it. And we've also made some references to this multipath propagation. We said that, okay, the signal goes in multiple paths. So what we will see are two types of effects. The first one are what we call as large scale effects. When you move hundreds of meters, that is the large scale effects. So typically shadowing is a large scale effect. On the other hand, small scale effects are those that happen when I move from 20 lambda to 10 lambda to 20 lambda. In that order, in that range of, so the ranges are very different. Small movements, if I move from this end of the table to the other end of the table, my shadowing will not change. But there are parameters that will change, and those that change with small perturbations of your position are referred to as small scale effects. Now, how small are the perturbations? I think we did a simple calculation last time, but let's do that again. If I'm talking about 900 megahertz, my lambda is 1/3 of a meter. We're talking about 20 lambda, that means around 6 meters. So small variations, that is outer limit, that is small scale variations. Now on this one you're talking about variations over 1 kilometer, 200 to 300 meters. So quite a big difference in that. Now let's start by understanding what these parameters tell us. Free space propagation, it's a large scale. You can have free scale propagation over long distances, but free scale propagation happens line of sight. Right? There are no obstructions between the transmitter and receiver, line of sight. Now in cellular we never assume that there is line of sight, and so more or less everything else is non-line of sight. NLOS is non-line of sight. Non-line of sight could be indoor propagation, could be outdoor propagation. Both these are valid environments. Now what are the ways in which the signal propagates when you do not have line of sight? Again, I'm sure you would have seen it in physics, but I thought I would just mention it. This is described in the propagation article. So if I have transmitter and receiver, I do not have line of sight. So basically this path is obstructed. So therefore the only ways in which it can propagate is, the most important one is diffraction. That's the bending of electromagnetic waves around the edges of objects. Again, I'm sure you have done physics experiments in diffraction. This is exactly the same thing. So there is the bending, and this has to do with Huygens principle. Now the other type of mechanism by which the signal propagates is if you have very smooth surfaces, which can then actually reflect the rays. So that means you're basically changing the using the laws of reflection. Angle of incidence is equal to angle of reflection. So therefore it can be a complete change of path. Diffraction is just a bending. This is and of course there's a third mechanism which is also important, because reflection and diffraction alone do not account for all the signal that we receive. Then you go back and look at it. Okay, there are objects that are in your vicinity, large objects, which are not very smooth. So therefore they are not reflecting it in a uniform direction, but basically they are scattering the signals, some of which are beneficial to you and they reach. So the three modes of propagation: diffraction or diffraction, second is reflection, and scattering. All three have a role to play. All three have different roles to play, whether you're talking about outdoor or indoor, and again what type of environment that you are in, all of these. So when we go back and look at it, all of these have to be accounted for. Depending upon whether you are indoor or outdoor, they impact you differently. So the combination of these two gives you outdoor propagation models. Outdoor propagation models. Any outdoor propagation models that you've heard of? Hata model. Okay. So maybe just a name at this point, but let me just write that down. Hata model, like Hata model. So outdoor models. These are propagation models. Example, Hata model. And by the way, the breakpoint model also fits into this because it is a non-line of sight propagation mechanism, and maybe we can write it down here. Breakpoint model. And the actual models that are used for outdoor propagation are fairly involved. They have lots of parameters, they are characterized, but at the end of the day, these are large scale effects. So now moving over to the other side, we now say that, okay, now I know that multipath happens. What are the ways in which multipath which manifests itself? First of all, it's going to manifest itself as fading. That is number one. Second, it's going to manifest itself as time dispersion. The fading itself can be either fast or slow. That's two variations. It depends on your Doppler, the direction of which you are moving. Now, is the fading occurring along with time dispersion? So flat fading means that there is multipath, there is no dispersion. This is fading is occurring, but multipath is there, but there is no time dispersion. This is with time dispersion. Okay? And again, leads to different types of environments. One of the most common that we see is what is known as Rayleigh fading. So this is non-line of sight. It has got multipath present. Multipath, it can have time dispersion. It can have time dispersion as well. Time dispersion. So Rayleigh fading has got a small line of sight component. It's not no line of sight. There is a, so again, in the bigger scheme of things, we have large scale effects, small scale effects. Large scale effects deal with shadowing and basic propagation, and the small scale effects are caused by the different reflections or the different paths that are arriving. What is the phase difference between them? Are they adding constructively or destructively? Is there a time dispersion between these two mechanisms? So this is a picture that sort of gives us a broad perspective, and what we will do now is to build on this perspective. So the first thing that we are going to take up is how do we proceed with this mechanism. So the first one that we would like to do is statistical characterization of large scale fading caused by shadowing. Caused by shadowing. Again, this is just to introduce us to the notation, the mathematical framework, so that we start to think along these lines. So as we saw in the first lecture, the shadowing basically happens because there is a obstruction in the line of my signal path. So if I'm at position A, I get a good signal. If I'm in position B and C, there is there's a drop because of the obstruction. We also said that this can be visualized in terms of a circle of coverage. Because of obstructions, your coverage may reduce in some places. In some places, you may actually go beyond the circle. And that is what we said is the realistic scenario that will happen on the ground. This is what we said we will capture in terms of a statistical model of shadowing. Okay? So statistical model of shadowing. And this is what we would develop first, get a feel for what how we go about this, and then move over from the large scale the shadowing, modeling of shadowing, to the small scale effects. So that is our plan. If you can read ahead, this is I will suggest the appropriate reading portions. Please do start looking at the shadowing part, then we will move into the effects of small scale fading. Okay, thank you.